Bismillah ar-Rahman ar-Rahim. My dear students, dear followers, my colleagues, this is a new video about subsequences. An easy definition. Let us consider a function O from n into n, and this function is increasing. Definition: let un be sequence we call subsequence of un any u or n. So any sequence from this kind is called a subsequence of un. Just we need that row of n be a function from n into n, and it is increasing. Examples: if we consider un equal minus 1 power n times 1 plus 1 over n. In general, u rho n, which is equal minus 1 power rho n times 1 plus 1 over rho n, is called subsequence of un. Un here is of this sequence of un. I mean this sequence. At each time we change a row of n, we find a new subsequence. How many subsequences do we have? We have plus infinity subsequences, possible subsequences. Concrete applications: if we consider row 1 or row from n into n, such that for n we associate to n. This is an application from n into n, and it is increasing. So we get u to n equal minus 1 to n plus 1 over 2n. If we consider row from n into n, from n to n plus 1, this is an increasing function, and from n into n, then u n plus 1 equal minus 1 power 2n plus 1 plus 1 over 2n plus 1. These are subsequences. We have a property related to the function row. Here we have a remark. If we have row from n into n and it is increasing in French strictement croissant, in Arabic متزايدة تماما, increasing, then row of n is greater or equal n for all n in n. Here we start from 1. Even if we start from 0, we have the same thing. Proof: for n equal 1, sure we have row of n is greater or equal to 1. It cannot be different of this. There is no way, because row starts from n and lies in n. By induction, we suppose that P of n is greater of or equal n, and how about P of n plus 1? This is strictly greater than P of n, because row of n plus 1 is strictly than row of n because row is increasing. But row of n, by this hypothesis, it is greater than n. If we connect this with this, we get row of n plus 1 strictly greater than n. But strictly greater than 1, this means that greater than or equal 1. This is what we need. Proposition. If un is convergent to n, then all its subsequences u or n converge to n, to the same limit. Proof. Un converge to n, this is equivalent for all epsilon greater than 0. There exists a rank n 0 of epsilon from n, such that for all n greater than or equal n 0 of epsilon, this implies that un minus n less than or equal to epsilon. Anyway, u row of n converge to n. This is equivalent to, we need to prove this for all epsilon greater than 0. Can we find a rank n1 of epsilon from n, such that for all n greater than or equal n1 of epsilon, this implies that u row of n minus n less than or equal to epsilon. It is obvious. We need to find the rank n1 of epsilon, which satisfies the inequality, this inequality. So it is sufficient to take, since row of n is greater than or equal n, it is sufficient to take n0 of epsilon equal n1 of epsilon. Why? Because row n is greater than or equal n. So if it is true for n, it will be true for row of n. It is very easy. How about the converse? The inverse. The converse is in general false. This means that we can get subsequences convergent subsequences doesn't implies that un converge. We can prove it by giving a counterexample. This example, un equal minus 1 over n, admits many subsequences. For example, this subsequence, it's converged to 1, it is a constant, it is equal to 1, so it converges to 1, and u to n plus 1 also minus 1, and it converges to minus 1. Both subsequences converge to 1 and minus 1, but this sequence isn't convergent. Do we have a result that ensure the convergence of un based on the convergence of subsequences? The answer is yes, we have. This is a theorem. Let rho E start from n into n and E from E to K. We have this application. Rho E increasing. Rho E increasing. If U rho E of n converge to L, here we are in the situation of we have increasing and we have UN. UN is a real sequence. If all its subsequences, we have K subsequences, converge to L, then and n, the natural number, equal to the union from E equal 1 to K, the sets rho E of n in n, if this is true, then UN converge to the same limit L. How we can prove this? How we can prove this? Proof. We have U rho E converge to L. This implies for E varying from n to k. This implies that for all epsilon greater than 0, there exists n E of epsilon from n, such that for all n greater than or equal n E of epsilon, this implies that U rho E of n minus n is less than or equal to epsilon. So this is true because we suppose that all the subsequences which verify this condition verifies this law. The question, do we have for all epsilon greater than 0, there exists n 0 of epsilon from n, such that for all n greater than or equal n 0 of epsilon, this implies that un minus n is less than or equal. The answer is yes, it is sufficient. To take n 0 of epsilon equal the maximum on the maximum E less than or equal k greater than or equal 1 rho E of n E epsilon, and it will be true. Why? Because since we take n0 of epsilon, the maximum between this, we ensure that for any given n greater than rho E of n E of epsilon, this will be true, which makes it true. And to make this more easy, we can prove this result. Corollary. Suppose that U to n converge to L and U to n plus 1 converge to the same limit n. Show that UN converge to L. So, u to n converge to n. This is equivalent for all epsilon greater than 0. There exists n1 of epsilon, such that from n sure natural number, such that for all n greater than or equal n1 of epsilon, this implies that u to n minus l is less than or equal, and u to n plus 1 converge to l. This is equivalent for all epsilon greater than 0. There exists n2 of epsilon, such that for all n greater than or equal n2 of epsilon, this gives us this formula. Here, un converge to n. Why? Because for all epsilon greater than 0, there exists n0 of epsilon, which is the maximum between 2 n1 of epsilon and 2 n2 of epsilon plus 1. We take the maximum. And for what? For which? For all n greater than or equal n0 of epsilon, one has un minus n less than or equal to epsilon. Why? Because if n is greater than 2n1 of epsilon, n is greater than n1 of epsilon, so if n is greater than 2n1 of epsilon, this means that what? This means this is true. And if the maximum is 2n2 epsilon plus 1, we are here. And in both conditions, in both situations, we ensure that it is less than or equal to epsilon. You can discuss separately the cases, and you will be confident about this result. There is a very important theorem, sunrise or sunshine, the Bolzano-weierstrass theorem. This theorem is very useful, large use of this theorem, Bolzano-weierstrass theorem. Bolzano-weierstrass theorem. This theorem said if un is bounded, then un admits at least a convergent subsequence. What we know? We know that if we have a monotonic sequence and bounded monotonic sequence, non-decreasing and upper bounded, so it is convergent, non-increasing and lower bounded, it is convergent. A sequence which is bounded, this does not mean that it is necessarily convergent. In this case, if we have a bounded if we have a bounded sequence, we have it admits at least a convergent sequence, subsequence. We can show this theorem by the means of I will draw it. This is n, and this is un. Suppose that our sequence is bounded by these bounds, this one, A, un equal n, not just A. Un is between A and B. And without loss of generality, we can suppose that this sequence is just positive. So just to make the sharp here. A term UM is called the peak of the sequence, the top, the summum of the sequence of UN, if UN is less than UN for n greater than n. For all n greater than n, UN is less than UN. To better understand, this is the terms. We can consider this the first one, U index K1. This is, we suppose that this is the peak. All the terms that came before this one is less than. So verifies this formula. This is the peak. Others less than. We have here, this is the second peak. This means this peak is less than this one, but this is the first one. So all the terms that come before are less than. To verify this one. Now this is UK2. And we have here, we can get all what you can imagine. If we consider that this is a peak, so all the terms that came before, after UK3, and you can imagine we have two situations. The first one, the number of peaks is infinite, and the second situation, the number of peaks is a finite one. In the case what they are infinite, this means that it continue to be decreasing. This means that here we have something like this, UKN, and it continued decreasing and so on. If we take the subsequence, which is formed by these terms, so rho of n is equal kn. This k1, k2, k3, and so on. This is a decreasing subsequence, and it is lower bounded. Decreasing and lower bounded, this means that it is convergent. In the case of the number of peaks is a finite one, this means we have the last one. Suppose that we are here. This is the last one. If this is the last one, this means there is no peaks before. If there is no peaks before, we have here, this is the last one. UK3, for example, is the last one. We have 3, finite number, as an example. This is the last peak. This means we can get like this. We can get like this, like this, like this. But at a given moment, we have this situation. We have this situation. We have this situation, which is greater than this one, but less than this one. This is This is a peak, and this is the last one, which means what? If this is the last one, we cannot get peaks after. We are here. We are here. We cannot cross this one because it is a peak. But here, we can find less than this one, less than this. At a moment, we have more than this one, because this cannot be a peak, more than this one. And here we have less than, less than, less than, less than. A moment, we have something which is greater than this one, but less than this one. And we will continue like this. We cannot cross this line because this is considered as a peak. We cannot cross it. This line, we cannot cross it. Starting from here, we cannot cross it. But at each time, if we have a summum, we must find another which is greater. We can get this alls, but a moment we have a greater which cannot cross this line. This sequence starting from here is an increasing subsequence, and it is bounded. Since it is an increasing and bounded, this means that it is convergent. This is all for today, my dear students, followers. I hope that can be useful. See you next time, inshallah.